Okay, so this is Unit 6, Notes 3, which is our final notes of this unit. So today we're going to be talking about exponential decay, which is the opposite of exponential growth. So now instead of having things going to go up, they're actually going to go down. So let's take a look at this chart. It's going to be really similar to the one that you wrote down for exponential growth. So there it is. Go ahead and pause the video, write it down if you need to. Otherwise, I'm just going to continue talking through it. The general equation is y equals 6 times 1 minus r. So instead of 1 plus r, we have 1 minus r raised to the t power, where c represents the initial amount. R represents the rate of change, which is a decimal, and t represents the time. This is the same as growth, except the difference is we're doing 1 minus r. Again, our c is our y-intercept, and our graph is going to have to decay downwards. So really similar to yesterday. So let's take a look at some of these growth equations. So again, my best suggestion is to make a chart if you need to. I know we didn't do that as much yesterday, but if you need to take a look back into making a chart, you can just plug in values for x and have it decay upwards. Remember that value being multiplied out front, that is our y-intercept. So I know that I'm crossing the y-axis of this at 16, which is right here. So I know I'm crossing it at 16. Because it's a decay equation, I want it to go downward. Notice that thing in the parenthesis is less than 1, which means it's going to be going downwards. So when I plug in 1, that's the same as saying 16 times 0.75. And when I do that, I get 12. So I can plot that point there. The next one I get, I'm going to raise 0.75 to the second power. When I multiply all that out, I get 9. So we're going to keep sloping downwards. Next, when I raise it to the third power, then I get 6.75. So I'm going to go over 3, and then I'm going to go up 6, and I'm going to go up 3/4 of the way. Next, I'm going to plug in 4 for x. So I'm going to take 16 times 0.75 to the fourth power. When I do that, I get 5.06. So I'm going to go up to 5 and just a little above. So if you guys are noticing, our decay is starting to level out a bit. It's not sloping down as fast. Okay, that's that kind of ski jump effect. So next, when you plug in 5, you get 3.8. So I'm starting to get a pretty good picture of the slope. And eventually it's going to come close to the x-axis, but it's not quite going to cross it. Exponentials will not cross because there is no negatives involved. Okay, there are no negatives involved here. That's why we're never going to cross that axis. So let's go ahead. I think I'm pretty confident that you can do this second one on your own. Again, if you need to set up that chart, here are some good values for x. If not, you could also look at this way. Here's another way to look at exponentials. So I will tell you that your y-intercept is 18. So we're crossing the y-axis at 18. Again, that comes here. So we're taking that answer and we're multiplying it by 1/2 or 0.5. So we're dividing it by 2. So your next one will be 9. Then you take that answer and you multiply by 0.5. Your next answer, multiply it by 0.5. Your next answer, multiply it by 0.5. You're taking whatever answer you get and multiplying it by 0.5 again. That's what an exponential equation does. Okay, that's what we've been doing the past couple of days. So you could also do it that way if you don't want to enter it in the chart-wise. Whichever method you want to choose, go ahead and do it right now. Get that graph on that chart. All right, next, this one we need to actually set up the ratio itself. Okay, well, I know that decay takes this general form, and that's just from the beginning of our notes. So I'm going to plug in what I know so I can get that equation. So I'm going to do y is equal to 16 times 0.5, or sorry, times, getting a little ahead of myself, 1 minus 0.45 raised to the t power. So now I want to simplify out what's in the parentheses just to make my life a little bit easier. So that's 0.55 raised to the t power. So now what we're going to do is I want to go through and I want to plot the points. So if you want to go through and make a chart as so, feel free to do so. Okay, again, the good x values are 0, 1, 2, on the way down from there till you feel confident about your exponential shape. We're crossing the y-axis at 16. Again, our c is our y-intercept, so we're crossing at 16. And then I'm going to take that t and I'm going to let it be equal to 1. So I always put x and y on my chart. It's partly because I forget, but it's also partly because I want you to look at it as a coordinate point. Okay, so I want your x or your t to be going across there and your y to be going across the top. So when we plug in 1, that brings us all the way down to 8.8. So I'm going over 1 and up almost all the way to 9. Okay, for that second one, when you plug that into your calculator, now instead of just listening to me blabber, I really suggest that you're actually typing this into your calculator yourselves as well to make your life easier, to make sure you're doing things right. Okay, so when you plug in 2, you get 4.84. So I'm going over 2 and almost all the way up to 5. Then when I'm at 3, when you plug in 3 for t, you get 2.662. So I'm going over 3 and up 2 and about 2/3. And so again, we're starting to level out a little bit. Then when I go over 4, I'm going up 1.46, which is almost 1.5. And lastly, for number 5, I'm going up 0.81, which is almost to 1. So now I can go through and I can draw in my exponential. There she be. So what I want you to do is I want you to actually set this one up yourself. Again, here's that general form of a decay equation. The biggest thing students forget is that they need to subtract there. So make sure you're taking 1 minus what the rate is and not just plugging that rate in. Your rate in the parenthesis, whatever's in the parenthesis, should be less than 1. Okay, that's your goal. So go ahead, write this equation, and then I want you to graph it. Okay, it'll most likely be on the quiz at the end of the video. Okay, so let's start applying these things because that's where math makes the most sense. So a fully inflated raft loses 6.6% of its air every day. The raft originally contains 4,500 cubic inches of air. All right, that's fair enough. So now we need to write an equation. Okay, they didn't give us an equation, so I have to write it itself. If we're losing anything, we're probably going to decay. We're going to go down with the amount we have. So I know I want to use that general form of a decay equation. Okay, so let's plug in what we know. Well, we don't know why. Our starting value is right here. Here's how much air we're starting with, which is 4,500. 1 minus our rate. Now that rate is in percentages. So again, because it's in a percentage, I want you to convert it to a decimal. So you're going to move that decimal point over 2 places. And then you're going to raise that to a t power. We don't know what the time is yet, so we're going to leave it at t. The last thing I want to do is simplify what's in that parenthesis. And when I do that, I'm left with 0.934 raised to the t power. The second part of this question asks me to estimate how much air will be in there after 7 days. So my time is 7 days. So I'm going to rewrite out this equation, but instead of writing t, I'm going to write that 7 days because I know that's the time period that I'm looking for. So that's raised to the 7th power. So you can go ahead and plug that into your calculator. If you plug it in exactly how it is on here, that will lead you to the right answer. A lot of you, when you're plugging in the exponents, are going to have to use that caret key. So if you're still unsure how to do this, please ask me because I'm just going to assume you can punch it into your calculator at this point. When you put it into your calculator, you're going to get 2790. And let's round to 2 decimal places, 0.23 cubic inches of air. So because it's a word problem, again, we want to make sure that we put that label on it. So that right there is your answer. Okay, we're done with that one. Let's take a look at number 6. During the past several years, the population of Campbell County, Kentucky has been decreasing. There's a very important word, at an average rate of about 0.3% per year. Okay, so then it gives us the starting population. So whenever it says the population was and it gives us a date, that's probably our starting point. So we want to write a decay equation that represents this scenario and then write, or assuming that a trend continues, we want to write the equation with a time so we can figure out what the population will be next year. So let's go ahead and do this. So we have y is equal to, our starting value is 88,647. Then in our parentheses, we're going to have 1 minus our rate. Now, right now, we're at 0.3%. So I have to move that decimal over 2 places. So I'm actually going to have 0.003 when I convert that percentage. And that's going to be raised to some sort of time, at least when I'm first writing out this equation. So then to simplify it down, I get 88,647. Then 1 minus 0.003 is going to give me 0.996. 7 raised to the t power. Okay, but then I want to know what the population is in 2013. Some of you might say, well, hey, that doesn't give me a time. It does. Our starting value is in 2000. So how many years passed between 2000 and 2013? Well, 13 did. So now we're going to rewrite out this equation, and instead of writing t, I'm going to write 13. So I'm plugging in that exponent of 13. And when I punch that into my calculator, I get 85,251. And then I want to label it with people. Talking about a population, so that's representing people. All right, let's take a look at number 7. What I'm going to do is I'm going to set up the equation for you. Then I want you to figure out for me how much the donations were 5 years after the start of the recession. So when you're reading through this word problem, you're noticing that donations dropped. That's a negative term. It's going down, which means I need to use exponential decay. So let's write that equation. So y is equal to, then we look before the recession started. So this is representing our starting point right here, this $390,000. That's our starting point. And then it's dropping by 1.1% per year. So we have to change that into a decimal. So I'm subtracting off 0.011 in the parenthesis, and that's going to be raised to some time t. So then when I write out the equation, I can subtract what's in the parenthesis. When I subtract what's in the parenthesis, I get 0.989 raised to the t power. So I want you guys to just pause the video, and I want you to try and see what it's going to be after 5 years. So now instead of having t, you're going to have 5. So try that out on your own. See what answer you get. Make sure you label it, and this label is going to be money. Last but not least, let's look at this last problem. So we're talking about a plasma TV, and that should say inches, not ink. That doesn't make any sense. All right, so it's depreciating. Whenever you see the word depreciate, that means to go down. Appreciate means to go up. Depreciate means to go down. Okay, so we're talking about going down here. So I want you to read through this word problem, use 5,000 as your starting value, and I want to see if you can figure out what the value is going to be in 4 years. So set it up and solve it as yourself. Once you're done with that, go ahead and take the quiz.